Welcome back. Having looked at the energetics and thermodynamics of nucleation in the previous lecture, in this lecture, we will look at nucleation rates in electrodeposition. This is always a good approach. First, think through the energetics, then come to the kinetics. In the previous lecture, we had discussed this kind of a plot. You plot Gibbs free energy in the y-axis as a function of number of atoms. And you also vary the overpotential. What we see is that the Gibbs free energy as a maxima, and with this maxima, we associated a structure called the critical nuclei and the delta G associated with the critical nuclei. So whenever there is an activated process, that is the delta G, free energy is increasing and then decreasing, this activation energy controls a particular kind of process. In this case, it controls the rate of nucleation, which is indicated by J. So as the number of nuclei increases with time, J indicates that the um, rate of nucleation. So this rate is controlled by the delta G. So this kind of the way to describe these activated processes goes to the early days of Arrhenius and so on. So in general, we can fit J to some such expression. You have A naught, the interpretation of A naught can be complex, depends upon the situation. But in general, J is related to some exponential of this kind of function. So this is the activation energy, in this case, the Gibbs free energy associated with the formation of a critical nucleus. And using via models concerned with 3D nucleation and growth or 2D nucleation, we derived some expression for delta G, and we can connect J to this delta G. We did this for 3D nucleation as well as 2D nucleation. Moving on. So what is that we want to recognize is that J is crucially dependent on the overpotential. So in electrochemistry, the main knobs we have is the control of potentials, right? So you can significantly suppress kinetics or significantly enhance kinetics by changing certain overpotential. So what we see is that we are trying to understand this relationship, how J depends upon the overpotential. So if you do some experiments, what we see is that the rate of nucleation in this case increases significantly at a particular overpotential. We call this um, critical overpotential. This is the overpotential beyond which the nucleation rate uh, increases dramatically. Till you reach this overpotential, there is no significant nucleation. It's hard to detect these nuclei experimentally, let's say. And then beyond a particular point, the nucleation rate increases significantly. So there are different names and different procedures associated on how to identify eta critical. We will not go into that, but we can ascribe some overpotential. Uh, so see, when you say increase, so we are talking about increase in overpotential. We are talking about the absolute quantity, because here the overpotential itself is a negative quantity. So when we say this quantity increases, the absolute of this quantity increases, what we mean is that um, this negative quantity increases because we are thinking about uh, cathodic electrodeposition. The electrodeposition occurs at the cathode, so these are all negative numbers. So this is an important feature. So there is some minimum overpotential that is required for observing and measuring nucleation. Moving on, what we see is that from the expressions projected in the previous slide, we see that the nucleation rate is independent of time. Okay, so within the models which we have derived, nucleation is independent of time. So this sort of makes sense, especially when you divide the nucleation and crystal growth to early stages of crystal growth and late stages of crystal growth. In the early stages, we are usually focused on nucleation. This is the main physicochemical event that occurs. But at a later stage of the process, growth dominates. There is perhaps no further nucleation, or at least the nucleation events are much less, and the atoms typically attach to pre-existing nucleus, and then we are focused on the growth of pre-existing nuclei. So in these stages, that the nucleation rate is independent of time is a reasonably good observation that is also observed in experiments. So these experiments can be quite complex because um, the after nucleation, the rates can be very fast. How to detect the size of a critical nuclei is a grand challenge. Okay, so it's not trivial exercise. So, but one nice thing about uh, electrochemical systems is that you have a good control in the sense that the knob which you can change is the O potential. Supposing you are in a O potential wherein there is significant nucleation, you can suddenly um, decrease the O potential so that nuclei is no longer formed. Okay, with such kinds of experiments, you can measure the number of nuclei with respect to time. Because at some particular time point, let's say, you abruptly bring down the O potential, the absolute magnitude of O potential, so that there's no longer new nuclei that are formed. So, with that kind of experiments, you can measure the number of nuclei with respect to time. But what we observe is that for most O potentials, you, it is a linear rate. Okay, that the rate is independent of time. That is, the number of nuclei is linearly proportional to time. So let's again summarize. From the previous lecture, we have derived these kinds of expressions. So from these expressions, what a quantity which we are interested in is n critical, the number of atoms associated with the critical nuclei. So how is this typically done? Okay, so you via some models, okay, either let's say 2D nucleation and growth or 3D nucleation and growth, we derived expressions for delta G. Using these expressions, you we when we have J plotted against O potential or square of the O potential, using these expressions, we can get an idea of n critical because this is connected with this quantity, that is delta G is connected with n critical. And you typically, when you have an activated process, the rate of the processes is connected to delta G. So in effect, J can be connected to n critical. So that is what we show in this expression with very simple mathematical manipulation for 2 denucleation. You can get this quantity. So you typically plot either for 3D nucleation or 2D nucleation. You plot ln J versus 1 by eta squared. Okay, so the slope gives you an via the slope we can find out this particular quantity. So this is an useful quantity to know, and as we had uh, shown in the previous lecture, this quantity is fairly sensitive to the overpotential. In the next lecture, we will look at certain other aspects of the growth of nuclei.